So in the beginning of section 4.1, Intro to Hypothesis Test, they have this study of mice weight gain sleeping in the dark or sleeping in the light. So mice weight gain, light or dark. So I went and grabbed that data from StatKey, and so I got a couple different versions of it we're going to look at to think about this. And we'll try to define our variables, population, and then see where we end up for the hypothesis test. Okay, so here I have some summary statistics. So the original data had mice that were exposed to light at night when they should have been sleeping. And the quantitative variable is their weight gain over a given period of time. And then some of the mice, however, slept in the dark. And then we have data about their weight gain over that same time period. So we have mice that slept under lit conditions and mice that slept under dark conditions, and they were fed a special diet trying to get them to gain weight. And so we have a list of their weight gain over those times. So we can see for the light mice, the average weight gain was 6.7, and for the dark mice, the average gait gain was about 4.1. So there is a difference in the sample. Now, just because there's a difference between the two populations in the sample, the two groups in the sample, doesn't mean that the difference is a big deal. Like when we looked at exercise, male students exercising and female students exercise, it looked like males exercised a little bit more, but it turned out when we ran the confidence intervals, they had similar ranges. So they could have been the same. We didn't really know. Side by side or histograms to kind of compare these two. We can see that the mice that slept in the light, there was a much wider range of weight gain there. And there were more mice that had a higher weight gain than the ones that slept in the dark. And box plot comparison, we can see that the mice that slept in the dark had a narrower range here. We can see that middle 50% here is between about 3 and 5 units of gain, whereas the light mice had a 50% range in the middle of between 5 and 9. So looking at this, I'm wondering, maybe light does help somebody gain more weight if they wanted to do so. So confidence interval. Now with the confidence interval, we're looking at the difference in their means. So if we take the mean for the light mice and subtract the mean for dark mice, we get 2 point something. And so that's what's being shown here. It's about 2.62 is the difference. So I'm now ready to define my population and parameters and take a look at what this confidence interval tells me, and then we'll look at running a hypothesis test. So we have population. In this case, it's mice. Parameter. In this case, we have a mean difference. So I'm going to call it X bar D, kind of like before. And it's the mean of the mice that were exposed to light. I was going to do D for dark, minus the mean, I guess I'm just going to put dark here, and diff here. So the difference in the means, mean of the mice, mean weight gain of mice that are exposed to light, mean weight gain of mice that are exposed to dark. So X bar L is the average weight gain and it is really important that we look at a problem and define what's the population and what does each variable mean. Otherwise, we have no idea what's going on. So average weight gain of mice exposed to light at night. X bar dark is the average weight gain of mice not exposed to light. So we took these two different parameters and subtracted them to turn them into this one new parameter. So that's my new one right there. So, oops, and I have an error in my notes here. I'm talking about a population parameter at the moment, not a sample. And so these should be mu's, not X bars at the moment. Not until I start talking about the sample numbers do I get to X bar. So it should be mu difference, population, population mu, population mu, population mu, mu diff is the difference of the averages. Not the average difference, that would be something else. Difference of averages, light minus dark. And all I'm doing right now is I'm just going to calculate a confidence interval. What do we expect based on this sample the average difference to be? So we're going to do a 95% confidence interval. That's going to answer what do we expect the average difference to be, or the difference of averages to be. And looking back at StatKey, this data wasn't already there. I had to steal it from another location. So I don't have a link to share out to this at the moment, but I will have something similar in a minute. So I put the data in here, and then I generated thousands of samples. So that's the procedure for confidence interval and StatKey. And so StatKey claims that that difference is somewhere between 0.673 for a 95% confidence interval and 4.614. Pull that off the side for a minute so I can put in my notes. So we expect the difference interval notation to be, let's see it, hang on, 0.673 low up to 4.614 is my 95% confidence interval. And if we look back at the sketch from StatKey, here, 0 would be no difference, is not in the interval. So the question, so a different question than what is the average range for the difference? Well, we think that's between about 0.7 and 4.6 is going to be the average different in weight gain, being exposed to light or not being exposed to light at night. So somebody might say, okay, is that difference significant? Meaning, could it be there's really no difference, that a difference of 2.6 isn't enough to be important? And I would say, well, no difference would be 0, and 0 is not in my confidence interval. And we might say, well, let's make a bigger confidence interval. So we could change this from 95 to 99%. And 0 is almost, but not quite in a 99% confidence interval either. So does this imply that there is a significant difference in weight gain if the light is left on at night? And the answer is yes, there does seem to be a difference. That no difference is not in the interval, so there does seem to be a difference. So just a side note here, since 0, right, mu diff is not in the interval, then there seems to be a significant difference in weight gain if the light's on. So I read this study, I saw this report, and I told my mom, I said, hey, it looks like leaving the light on at night could make people gain more weight. She's like, oh, shit, I better not sleep with the lights on anymore. And then I mentioned there seems to be a significant difference. And then she thinks about that for a minute. She's like, what do you mean by significant? It's like, oh, good question. What do I mean by significant? And that's where a hypothesis test is. It helps us measure how likely or unlikely it is to have 0 in the interval or not in the interval. So now we're going to jump over to a hypothesis test, and that's where this data actually lives. So now we're going to try and get to the idea of what does it mean to be significant? Because sometimes a difference of 2 is a big deal, but other times it's not a big deal. So hypothesis test. Question. Does sleeping with the light on to weight gain? Or to more weight gain, I guess. And so the option is the light's on or off, right? So this is a little more complicated because we have to consider the difference in gain between having the light on and not having the light on. So to get a little more technical here, is the difference in means, is the difference in means greater than 0? Because if the difference is 0, there's no difference. So that question right there says, is the difference in means greater than 0? So should that be a null hypothesis or an alternative hypothesis? Any thoughts on that?
An alternative.
Yeah, it's an alternative because there's no equals. If someone came out and said, hey, there's no difference, it doesn't matter whether the light's on or not, that would be no difference would be equals 0. So that would be the null. This one has no equal sign in it based on the way the question was phrased. And so this one would be an alternative. So I'm just going to state these in the shorthand notation. Null hypothesis is H with a 0 subscript. Alternative hypothesis is either HA or H1. And in this case, my question ends up being the alternative, and that's usually what happens, but not always. Difference is greater than 0. And the null hypothesis could either be the opposite of this, which would be less than or equal to, or it could just be equal to. And I usually go for the simpler version, which would be just equal to. And again, if it's equals 0, there's no difference. 0, no. So interpretations here, like common language, no difference. And let's see what's missing here. My mu diff is the light minus dark. I should put that up here somewhere. So mu diff is mu light minus mu dark. And StatKey kind of picks that for you. So we're going to go over to StatKey to take a look at this. And this is located in the randomization test. Yeah. So I'm going to put this link in the chat. So this is the mice weight gain data. And I got it by going to randomization test for a difference in means. This is the first example in the book. They take a look at it in the first few sections. When I first get to this page, it talks about leniency and smiles. I'll talk about that study later. I want mice weight gain. So we got to switch data sets here. And the order that these are subtracted here depends on how the data is input. So the light mice data came first. So that's their X bar 1, and the dark came second. So that's their X bar 2. So it's always the first group minus the second group when the data was put in. If you wanted to switch that, you'd have to change the order. And these do have to be sorted, otherwise StatKey gets all messed up. So let's get out of there. So when we run a hypothesis test, on many instances, we have to do two things to get started. We have to get the right data set. So that's either look for this data set in here, or edit and add your own. And then we often need to set the null hypothesis. Now, with the difference, they preset that for me. And I just want to compare that to what I have here. I have that the difference of the means is 0. So here, my difference is light minus dark. So mu light minus mu dark is 0. That's my null hypothesis. StatKey restated it by just adding this mu dark to the other side. So here it's subtracted. If I add it to the other side, that's equivalent to saying that the average weight gain for light mice is the same as average weight gain for dark mice. And whenever we compare a difference, that's pretty much the standard null hypothesis. That they're equal. Equal means no difference. And we run the hypothesis test. So we've got the right data, we've got the right null hypothesis, and then I want to generate. And then the test we pick depends on our alternative. So look back at the alternative. Our alternative is greater than. Greater than is to the right. We think it's bigger than 0. All right, so that implies a right test because it's greater than. So I select right. Once I do that, StatKey throws a number over here, and it picked a number that goes with a 2.5% uppercase limit here. What I do next is I put my sample data in place here. Right, so that was like, I think, step 5 in my notes back here. So I found my sample data. I made sure I had the right null and alternative hypothesis. The order of selecting the test and generating the samples, I think I might have done those backwards, but I don't know if it matters. And then we put the sample statistic on the x-axis. So that's what we do next. So our sample statistic is the 2.62 here, so that goes down at the bottom. 2.62. So what this tells me here is that if we expect there to be no difference in weight gain with the lights on or not at night, the chance of getting a sample with a difference of 2.62 or higher is about 0.019 or 1.9%. So I'm going to draw a picture of that. And I am running out of room, so new page. So So I draw my best bell-shaped curve. Alternative is taking a screenshot of StatKey. And so here in the middle, I have my difference of 0. And that's saying that mu light equals mu dark. My sample data ended up being way out over here. That was 2.62. That was my X bar for the difference. And this D is dark. And StatKey says that the chance of getting a sample like this, that's not a 2, the chance of getting a sample like this or higher, that's what a right tail means. So this is now a probability on this side. Probability was 0.019. And StatKey is always going to give that as a decimal. I always like to rewrite it as a percentage. So that would be, move the decimal twice, 1.9%. So in our probability notation from before, this would be the probability of having a sample mean for the differences that is more than 2.62 if we expect the mean difference to be 0. So it's a conditional probability, and we think it's about 1.9%. Now, the usual cutoff for being unusual is about 5%. So if we get a probability that's smaller than 5%, we say, huh, this seems unusual. So what does that mean? So two things. I want to just explain what this probability means again in terms of putting that in more plain language. So the chance of finding another sample with a difference of means that is greater than 2.6, when we were expecting a difference of 0, no difference. That's important. It's about 1.9%. 1.9% chance that would happen. So this seems unusual. It's less than 5%. So 1.9% is less than 5%. So this seems unusual. If it's unusual, then one of two things is the problem. Either we just got a weird sample, and that certainly happens, or this expectation that the difference is 0 is not correct. So this is evidence that there is a difference that's greater than 0. This is evidence that light causes more weight gain. If we get right down to it. In mice, yeah. Yeah, and lots of studies are done on mice, and we wonder, does that happen with humans too? So that would be like the next stage. Okay, we should check this out with humans. This is evidence that light causes more weight gain in mice. So this is evidence for the alternative hypothesis. It's evidence against the null hypothesis. So in a situation like this, we often say, reject the null hypothesis. Hypothesis. So the evidence does not support the null hypothesis that there's no difference. This indicates that there probably is a difference. Huh, yeah, predator versus prey, that's a good point. There's definitely differences in the biologies of predators and preys. Good point. All right, so again, we're trying to get used to, number one, what is a hypothesis test? Two, how do we run a hypothesis test? So I just have a couple other examples I want to take a look at before we run out of time. And I'm not going to run through the whole thing. I'm just going to get them started to look at how we deal with it. So